Hello everybody. In this video, we're going to talk about topic number 4, atomic mass and molar mass. We'll see some calculations in this topic. First thing is about periodic table. We saw a periodic table before, and we know that this number is the number of protons for the element. And this is a chemical symbol, and this is a name. And what about this number? This number actually is the atomic mass of this element. And if you check these boxes in periodic table, you can identify the atomic mass for each element. Okay, so how do we get the atomic mass? Before we talk about the calculation, we do have to define it. Okay, atomic mass is defined as the average mass of the isotope according to the natural abundance of each isotope. In other words, you do have to have the information regarding natural abundance of those isotopes in order to do the calculation. So how do we get the natural abundance? Well, you have to use mass spec. Okay, this picture shows you a very basic mechanism of how mass spec instrument works. Well, you introduce your sample from this side, and once the sample get into this chamber, it will be heated up, okay, to very high temperature. So those atoms will be ionized to charged particles. All right, those charged particles will fly into this chamber. Once they get into this part, which is a pair of very strong magnets, the charged particles from different isotopes will fly into different direction. Okay, and then they will arrive at the detector in a different path. Once they arrive at the detector, then the computer will do the calculation for you to identify the natural abundance. So eventually you will see a diagram like this. This diagram shows us the two isotopes of chlorine. Chlorine 35, natural abundance is 75.77%. Chlorine 37, natural abundance is 24.23%. So this natural abundance comes from the y-axis. And how about the atomic mass for each isotope? Well, they can be identified on the x-axis. Okay, so for chlorine 35, the atomic mass is 34.97 AMU, and for chlorine 37, it's 36.97 AMU. We talked about AMU previously. 1 AMU is defined as 1/12. Okay, let me write it here. 1 AMU is defined as 1/12 of the mass of one carbon 12 atom. Okay. If you do the calculation, you will see that 1 AMU is a very small number. But again, the actual value of 1 AMU is not our concern. We'll talk about the AMU again once we talk about the molar mass. But here, we just need to know that 1 AMU is 1/12 of the mass of one carbon 12 atom. All right, now we know the information about the two isotopes of chlorine. So let's use this as an example to calculate the atomic mass of chlorine elements. Okay, as we defined that atomic mass for an element is average mass of the isotopes, okay, based on their natural abundance. So we developed this equation for us to do our calculation. Atomic mass for an element equals to the fraction of isotope 1, means natural abundance of isotope 1, times the mass of isotope 1, which is this one here, okay, if you are talking about the chlorine, plus the fraction or natural abundance of isotope 2, right here, times the mass of isotope 2, right here. And if you have a third isotope, then you just continue the addition of this fraction of isotope 3 times mass of isotope 3 and go on. Okay, so here we will use the chlorine, the two isotopes of chlorine as an example to demonstrate. So let's set up the equation for us to do the calculation. So for the atomic mass of chlorine element, okay, that equals to, I'll write the chlorine element, that equals to, well, the first isotope, chlorine 35, natural abundance is 75.77%. Remember, this is a percentage, okay? In order to get the value of the percentage, you have to divide this number by 100. In other words, 75.77%. That equals to 0.7577. Okay, and 24.23%. That actually is the value. The actual value is 0.2423. Okay, we need to keep this in our mind because a very common mistake in this calculation is to just use the 75.77, the percentage, as the fraction of the isotope. That's not true. Okay, we should use the actual value of the percentage to do the calculation. All right, so let's start the calculation of chlorine element. So fraction of isotope 1, fraction of chlorine 35, that's 0.7577 times the corresponding mass of isotope 1, chlorine 35, 34.97 AMU. All right, so this is the first part, plus the fraction of isotope 2, fraction of chlorine 37, that's 0.2423 times the mass of chlorine 37, 36.97 AMU. All right, so this is how we set up the equation. Okay, now let's do the calculation step by step. Again, please, since we've already learned significant figures, we need to follow it. Okay, so I'll calculate this part and this part, and then I'll add them together. Okay, so for this part, if you do the calculation, that will give you 26.496769 AMU. Okay, well, you can keep these digits as many as you want, but you have to highlight the digit, okay, with the right significant figures or decimal place. All right, remember, this is a multiplication. Therefore, this number, the significant figures of this number should follow the number with the fewer significant figures. This one, 4 significant figures, 4 significant figures. So this number, this intermediate answer should have 4 significant figures. Therefore, I need to highlight 9 to tell me, okay, so this number should have 4 significant figures, 2 decimal places. All right, we're not done yet. This is the first part. Then the second part comes from this part. If you do the calculation, that's going to be 8.957831. All right, AMU. Now, again, significant figures. This one, 4 significant figures, 4 significant figures. Therefore, this number is supposed to have 4 significant figures. Of course, keep the digits as many as you want for the intermediate answers. So I would like to highlight 7. Okay, all right, now the last step is the addition. Remember, when you do addition, the final answer should have the same decimal places as the one with fewer decimal places. Okay, so that means this number, since it is supposed to have 4 significant figures, that means it will have 2 decimal places. This number, it is supposed to have 4 significant figures. That means it is supposed to have 3 decimal places. That means for the final answer, I'll do the addition first. That is a 35.97 4, 5, 4, 6, and you can keep going. But I think 4 decimal places here right now is good enough. Okay, so AMU. Let me erase this parts. Okay. All right. Now, because this number has 2 decimal places, this one has 3 decimal places. This answer should have 2 decimal places, right? This one has fewer decimal places. Therefore, you highlight that, and that will tell you you should drop the tail. That give you the final answer, 35.45 AMU. All right, so this is the atomic mass for chlorine element. Okay, this is how we do it. One more example about the calculation. Now this time it's neon. Neon has 3 isotopes. This one here, this one here, this one here. Okay, the atomic mass for each isotope and the natural abundance of each isotope has been given. So let's do the calculation. Well, according to what we saw in the previous slide, we know the calculation equation. So let's set it up. So for neon, that equals to, well, isotope 1, let's see this one here. That is, again, let me write this down. Okay, how about this? 90.48%. You can write down percentage when you set up the equation, but when you do calculation, you have to convert this percentage to its actual value times 19.9924 AMU. This is the isotope 1 plus, all right, isotope number 2, natural abundance percentage 0.27%. Times 20.9938 AMU. All right, now this element has 3 isotopes, so we have the third part, which is 9.25% times 21.9914 AMU. So this is the equation. Now let's do the calculation. Like I said, when you do the calculation involving percentage, you have to convert that to the actual value. So essentially it would be this number divided by 100. Okay. All right, let me write this down. So 0.9048 times 19.9924 AMU plus, okay, this one is a little bit small, 0.0027 times 20.9938 AMU, okay, plus 0.00925. Oh, sorry, I got one more. It should be 0.0925 times 21.9914 AMU. Okay. All right. Now what you need to do is just do the calculation step by step. For this part, it gives me this answer, 18.08912 AMU. Okay. Now significant figures, 4 significant figures. Well, this one has 6, so this intermediate answer should have 4 significant figures. What I would like to do is I highlight 8. Okay, now this part gives you a small number, 0.05668326 AMU. Again, you can keep digits as many as you want. Now this one, 2 significant figures, 6 significant figures, so this one is supposed to have 2 significant figures. So I would like to highlight 6. All right, the third item right here, that equals to 2.034 2045 AMU. Okay, 3 significant figures, 6 significant figures, so we are supposed to have 3 significant figures. So I would like to highlight 3 in this case. All right, now you add those 3 items together. That gives you 20.1800 AMU. Now let's consider the significant figures or decimal places. This is the addition, okay? So we need to consider the number with the fewest decimal places. 2 decimal places, 3 decimal places, and 2 decimal places. So the final answer is supposed to have 2 decimal places. Okay, so that tells us the final answer should be 20.18 AMU. All right, so this is this example. Now atomic mass. This is how we do atomic mass. Okay. The next thing is about the molar mass. Okay. This slide shows us some very important concepts before we start the calculation involving molar mass. Okay, well, 3 things. The first one is the Avogadro's constant. Okay, the Avogadro's constant is the number of the carbon. Oh, sorry, let me use this. Is number of the carbon atoms in 12 grams of pure carbon-12. Okay, and more specifically, that means for 12 gram of pure carbon-12, how many carbon atoms it has? Well, it's right here actually, but let me write this down, okay? So this is Avogadro's constant, 6.02214 times 10 to the 23. This is Avogadro's constant, okay? So, well, as you notice, now this number is huge. Okay, so it's not always easy to use this number all the time. So in order to make our life easier in chemistry and science, we define this as the mole. Okay, so that's the second concept that we're going to talk in this on this slide. We define if you have this much of particle, then we define it as the 1 mole of this particle. It's like if you have 12 eggs, then we said you have 1 dozen of eggs. Okay, so if you have 6.02214 times 10 to the 23rd iron atoms, then we would say you have 1 more of iron. Okay, so this is the mole. The next thing, the third one, is the molar mass. Okay, how do we define molar mass? Well, the molar mass of an element is numerically equal to the element's atomic mass in AMU. What does that mean? Well, if you take a look at this one here, okay, well, we know that this is the atomic mass of the chlorine. That's what we did in the previous slides, 35.45, and in the previous calculation, we said that this is the atomic mass is 35.45 AMU. And according to the molar mass definition, the molar mass of chlorine is numerically, with the molar mass, the unit is gram per mole, is numerically equal to the chlorine's atomic mass. In other words, the molar mass of chlorine is 35.5 gram per mole. Okay, another way to describe this is if you have 1 mole of chlorine atoms, then the mass of this much of chlorine atoms would be 35.45 gram. Okay, so that's what it means. Okay, and how do we identify the molar mass or atomic mass in chemistry? Well, again, from a periodic table. Well, different periodic table will give you will present the atomic mass slightly differently. But usually, if you got a periodic table, you can always see the example. Okay, so this is the example shown on one of the periodic tables I found online, and you can see, okay, it shows you where you can find the atomic mass. Okay, right here. Okay, so that means 1.008 is the atomic mass for hydrogen. So that means 1 mole of hydrogen atom equals to 1.008 gram. That's what it means. Well, again, this slide shows us three important things: Avogadro's constant, mole, and molar mass. Okay, so how do we use them for our calculation, especially the calculation involving number of the particles, the mole number, and the mass? I believe this diagram, okay, can guide us through the calculation. Okay, so in the next two slides, I'm going to show you some examples about the calculation by using this chart. All right, first one, calculate the number of the atoms in 2.45 mole of copper. Okay, well, element is copper, and you have 2.45 mole. So what you have here is the mole number, and it's asking you to calculate the number of the particles, particularly its number of the copper atoms in this case. So you need to focus on this part. Okay, you need to use the Avogadro's constant between this one and this one to do the calculation. So let's set up the equation. Well, you have 2.45 mole. And we know, according to Avogadro's constant, 1 mole of copper will have 6.02214 times 10 to the 23rd copper atoms. Okay, so we want to get rid of mole and convert that to the number of the particles. All right. Now, so we use the Avogadro's constant, or this part as the unit conversion factor. Okay, 2.45 mole of copper. Okay, and according to Avogadro's constant, 1 mole of copper will have 6.002. Oh, sorry. Okay, 6.02214 times 10 to the 23rd copper atoms. Okay, so in this case, you can cancel the mole, and then the final answer, you know, if you say that it's a unit, and then that's going to be the copper atoms in this case. So that will give you 1.48 times 10 to the 24th copper atoms. Okay, remember, final answer, 3 significant figures, because this number has 3 significant figures. Again, please ignore the significant figures of the constant. All right, this is the first practice. Second practice, how many moles of iron do this many of iron atoms represent? In other words, you know the number of the iron atoms. It asks you to calculate how many mole you have for this many of iron atoms. Again, we need to use the Avogadro's constant, or this one, but in the opposite way. Okay. In this problem, we did the calculation to this direction, but in this question, we're going to do the calculation from your left side to right side. All right, let's set up the equation. 8.2 times 10 to the 25th, okay, iron atoms. Now remember, the desired unit is mole, so when we use this constant, we need to flip it. What do I mean by flip it? That means Avogadro's constant should be at the bottom. 6.02214 times 10 to the 23rd iron atoms. This many iron atoms is 1 mole iron. Okay, now you can just get rid of this. Then the final units. Again, pay attention to the significant figures. I have 2 significant figures. more iron. Okay. Well, the reason why we have two significant figures is because this one has 2. All right, now let's take a look at more examples. Calculate the mole number of 3.56 kilogram of aluminum. Well, in this problem, you know the mass. It's asking you to calculate the mole number. Therefore, you need to focus on this part. And in order to do the calculation, you need to know the molar mass of aluminum. If you go to periodic table, you can find how much that is. Okay. Well, let's set up the equation. Remember, this is a kilogram. And in order to use the molar mass, gram per mole, you have to get the mass as gram first. So you need to do unit conversion from kilogram to gram. Okay, 3.56 kilogram. Convert the kilogram to gram. 1 kilogram, 1,000 gram. Okay, because you want to cancel the gram, you want to cancel the kilogram and keep the gram, so the gram should be on top. All right, now how do we use the molar mass? This unit right here. Remember, you want to convert mass to mole. So when you use the molar mass for aluminum, you have to set up the equation properly. For 1 mole of aluminum, okay, according to periodic table, the atomic mass for aluminum is 26.982 gram aluminum. Okay, let me write the aluminum here so you can see my calculation better. All right, now you can cancel the gram, and then the final unit would be just mole. And if you do the calculation, that will give you 131.94 mole. Okay, how many significant figures? Well, you have 3 right here, therefore we are supposed to have 3 significant figures. Okay, so you need to drop the tail after the decimal point, so that will give us 132 mole. We should avoid this kind of ambiguity, so because it does not show you where the decimal point is, so let's use scientific notation. So that's gonna be 1.32 times 10 to the second mole. All right, so this is this question. The last question, what is the mass of this many potassium atoms? In this question, you know how many potassium atoms you have, asking you to calculate the mass, so you need to use both Avogadro's constant and the molar mass. Okay, all right, let's set up the equation. 1.69 times 10 to the 22 potassium atoms times Avogadro's constant, this many of potassium atoms is 1 mole potassium. All right, now if you get rid of this part, and you will have mole. Now you want to convert mole to gram. All right, so you need to use the molar mass in this case. Okay, times, because you want to cancel the mole in the last step. So for when you use the molar mass of potassium, the mole should be at the bottom. For 1 mole potassium, it's 39.0983 gram of potassium. Again, this number comes from periodic table. And if you do the calculation, okay, I'll do this calculation step by step. For this part, it gives me 0.0280631 mole potassium, okay, times 1 mole potassium, 39.0983 gram potassium. Okay, you cancel the mole, and you get the answer as 1.09722 gram Okay. Oh, I forgot to mention significant figures for this intermediate answers, because you have 3 significant figures here, so we are supposed to have 3 significant figures. So I would like to highlight zero right here. All right. Now this is a constant because it's from periodic table. So the final answer should have 3 significant figures. Okay, so right here. So you need to drop this tail, of course, because it's 7 right here. So you need to round it up. That will give 1.10 gram. Okay, do more practice and let me know if you have any questions.